So when we start talking about logic functions, we have some basic functions that we'll refer to often. So we have a function that's called a buffer, and basically a buffer just isolates circuits. Okay, so there's logic symbols, and that's a logic symbol for a buffer. Okay, now again, if I draw that switch with the armature and the coil, that'd be a switch. And so when the input here is a 1 or a true, then the switch will close and we'll get a 1 over here, or a true state. And so we can, if we draw a little light, we call that Y, and then we call this input A, then we can derive what we call a truth table. And we have A and Y, 0, 1. So we say when A is 0 volts or false, the light will be off because the switch will be open. When we apply a voltage or apply a true, which is denoted by a 1, then Y will be true or illuminated. Okay. So that's your buffer. Then we have, if in this case where I showed this here, this is shown in a switch. In a relay logic, I'm going to draw that as a normally open contact, and then I'm going to associate this contact with some control relay, and then I will have the coil to the control relay, which is coil here is this same coil here, and the open contact is this switch here. The next logic we're going to action is a NOT. In a digital circuit, it's indicated like that or displayed like that, and it's this little dot on the end there that signifies a NOT. And again, we have input A, output Y. In this case, it's opposite. Meaning that I have a contact that's closed. So if I have some voltage here, 24 volts, I have input A here. So when I have 0 volts, no current, the contact is closed. But when I apply a voltage, say 5 volts, I generate a magnetic field. It pulls that armature up and opens a contact. So with 0 volts, I'd have a 1 over here. With 5 volts, I open that switch, and so now I've got a 0. So the truth table for this NOT looks like that. And if we're drawing this in a ladder diagram, normally closed contacts signify a NOT function. I move into an AND function. The digital logic symbol for an AND looks like that. Now we have two inputs, A, B, and an output Y. And essentially, you're saying that A and B have to be true to illuminate a light. So this is contact A, contact B. So when contact A is 0, contact B is 0, they're both open, so our light will be off. If I have contact A at 0 and B is energized, meaning that B is closed there, I still do not have a path. I still do not have a pathway for current because contact A is open. I energize A, and A will close. However, at this point, B is now open. So again, no pathway for current. But if I have both of them turned on, then I'm finally going to get an output. So this is the truth table for an AND function. Okay. And if I'm going to draw this in a ladder diagram, AB, that's an AND function. The next most common logic function is the OR function. In the OR function, the digital logic symbol for an OR looks like that. In this case, it's A or B. And right here, this what I'm drawing here is just the electromechanical relay. So I have A and B inputs now. So if A is 0 and B is a 0, then I have Y as a 0. As soon as I put a 1 on A, it'll close. I now have a pathway for current, so the light will turn on. So I'm going to kind of, hopefully by this point, you guys remembering that we covered this, that you've got the gist of it all. So anytime A or B is true, Y will be true. And that's the OR function. Now there's a logic, oh, excuse me, I forgot to add the context. If we're going to draw this in the ladder circuit, the OR function looks like that. The next logic function is the XOR. The digital symbol looks like this. Now this device, the outputs are high, the output is high when the inputs are different. When the inputs are different. So this one isn't as straightforward as the other 4 logic functions we've talked about. The XOR is different when the inputs are high. So when we draw this guy, we have a normally closed contact, a normally open contact, so here when we have our A, this is our A set of contacts, here's our B set of contacts. So in the truth table, if we have 0 volts applied here to A, 0 and 0, this contact will stay closed, and if we have 0 and 0 applied on our B contacts, this contact will stay open, this contact will stay open, so we have no pathway. So when A and B are false, then we have no pathway for electricity. Now if we put a 1 or a true on B, this contact will open, this contact will close. And if we have a 0 on A, they'll stay in their same state, and we actually have a pathway for current. So as you can see, they're different right now. A is low, B is high. I have electricity flowing to my light. Now let's put a true on A and a false on B. False on B, this contact here will stay open, this contact here will stay closed. A 1 on A will close that contact and open, and we'll have a pathway for current that way. Again, A is true, B is false, they're different. Then if we put a 1 on A, this guy will open, this guy will close, this guy will open, this one will close. And again, now I have an open contact on this rung, and an open contact on this rung, no current flow. So my truth table for an XOR is the output is high when the inputs are different. I ran out of page there, but if I'm going to draw this in the contact in contacts, that's how I draw it.